Okay, so we talked a little bit about regression and what the regression line is, and I'll do an example in Excel of doing a regression. So here I have some data on corn, a corn crop, and there's an X variable and a Y variable. And the X variable is the fertilizer, so that's the input into this problem, and the Y variable is the yield. So you can see, for example, the first row there was 100 pounds of fertilizer input, and the yield was 8,000 bushels of corn. So what this represents is, suppose that maybe we have, I think I have about 20, maybe about 20 points of pieces of data here, 20 data points. Maybe this represents like 20 different fields that we randomly selected, and then we put fertilizer, varying amounts of fertilizer into each field. So the first field, maybe we put 100 pounds of fertilizer, and then we check the yield at the end, and we get 8,000 bushels. And then the second field, we put 200 pounds of fertilizer, and we got also 8,000 bushels of corn, and so on. Okay, first thing we could do is we could graph this data. So we could go to Insert, and insert a, I'll do this kind of graph, and this kind, and there we get a graph. So you can see the relationship here between fertilizer and yield. Okay, and it seems to be, there seems to be a relationship, and it seems to be an increasing relationship. Okay, so now we might want to try and fit a regression line to this. Of course, we could try and draw it in, but we want to do regression line. We want to actually calculate the equation for the line as well. So let's do that. Let me, yeah, okay, I'll just leave this here. And so to do that in Excel, you go to Data, and there's this button over here, Data Analysis. If it's not there, you have to add it in, but it's here. And you select Regression from here. And then you have to indicate the Y input, or the output variable, or as they said, the response variable, which is the Y variable. So I put here for the Y variable, and the X variable, or the explanatory variable, here. And I want to indicate that I included labels in this analysis, so that because I used the word, I used row 3, I included row 3, so I leave that. And I want a line fit plot, as well as the other results that it will give me. So let's see what that looks like. So here's the plot. Actually, I don't like this kind of plot, right? So I want to change the style of the graph here. Let's see, how do I do that? Maybe I double click on this and change the type of chart over here, and use a scatter plot. You could use various types of plots, but I'm just going to use this one. There. Okay, so now we can see the original data, the blue dots, and we can also see the points, they're basically the regression line, as the red dots. And notice they call it the predicted yield. And the blue dot is the actual yield. So that goes along with what we were saying earlier. We said that's not it's not the blue dots are the actual points, the actual data points, and the red dots are what we would predict if we use the regression line. And the red dots sort of form the regression line. Okay, so that's an example of doing regression. Now, let's look over here for some of the, to get an idea about how good this regression line is in terms of predicting the output. So actually, the multiple r, or the r squared, will give us information about how good it is at predicting. I think it's the r squared that tells us that basically we're about 83% accurate. Okay, and this r squared, when we're doing this kind of regression, when we only have one input variable and one output variable, then the r squared is the capital R squared that you see here is the same as the or actually, what should I say? Is the same r that we just saw for the correlation coefficient. So if you squared that r that we saw in the correlation coefficient, you would get this as well. The correlation coefficient is a small r, and this is a capital R. They're not really the same thing, but in this case, they are. So that tells us that basically we're 83% accurate in our predictions. And we would also like to know the actual equation for the line. So I'd like to have like y equals, something like 2x plus 8 or something like that, some equation. Okay, so the equation we can get from here, these two values. So the b, is it bx? What is it? Anyway, so the equation will be y equals 3.2 approximately, 3.2 plus the slope, is 0.01 or 0.02, I'll just say 0.02 x. Okay, so that's the approximate equation. In other words, you can get the coefficients for a and b from here. Okay, so that's the equation of the red line here, basically. Okay? The other stuff that we get, like the t statistic there and the p-value and so forth, they have to do with how accurate we estimate these coefficients are. So it's 3.2, but are we really sure that it's, how sure can we be that it's actually 3.2? So if we want to be 95% sure about it, we have to look at these two values, actually. This is called the lower 95th percent, what is it called? Well, anyway, the lower 95th percent. So in other words, if we want to be 95% sure, we have to say that it could be as low as 0.2, and it could be as high as 6.2. Okay, so 3.2 is probably in the middle of that, and that's our best estimate. But if we want to be 95% sure, we have to use this broad of a range. And for the slope, this one, for 0.01, if we want to be 95% sure, we'll say it's between 0.013 something, whatever that is, up to 0.021, whatever that is. That will be the 95% confidence interval for that coefficient. Okay? That's what these numbers tell us. The t statistic and the p-value basically tell you the same thing that these tell you, that the 95% confidence interval tells you. What else do we have here? Nothing else that we really need here. Yeah. Okay, so I'll stop here.